Welcome to a lesson with Dr. Powell. We continue the example of finding the surface area of the top part of the sphere, the top cap, and we're looking at the way that we can just take the vector of aerial projections and write it directly in terms of d theta and d phi. We did that in the last video. And then here we actually wrote out the vector of aerial projections and we factored out the d theta d phi here. So to find the surface area, we need to be able to integrate over the range for theta and phi, where we're taking the length of this vector that we see here. So we already factored out this scalar. And then we could also factor out a -4 out of here, but since we're finding length, we're going to be taking absolute value. So all these -4s come out here to just be a +4 when we're finding the length. So let's kind of see how this is going to look. We factor out that, and then we're taking a square root of the things that remain. Now notice as when we square things. So here, when we square this, we're going to get a cosine squared, and square this, we're going to get a sine squared. And here would be sine to the fourth and sine to the fourth with a phi and a phi. Notice that when we add these two in a square, because of cosine squared plus sine squared is equal to 1, and it has a common factor of sine to the fourth after we're squaring, we're basically just going to have a sine to the fourth phi coming from the first two components squaring. And then over here, we're going to then over here on this side, we're going to square. We're going to square what we have over here, and we first notice that we have a sine phi, cosine phi, sine phi, cosine phi. It looks the same with the sine squared plus the cosine squared. So really, we could have written this part more simply, and we should do that before we square. When we do that, because sine squared plus cosine squared is just 1, so really this amounts to, after you factor out the -4, just sine phi, cosine phi. So that's really all we're squaring here. So we square that, and we actually just get sine squared phi, cosine squared phi. All right, and then of course we have a d theta d phi here. Sitting out here, I'm going to be integrating the theta and d phi. So let's work on simplifying this a little bit. More. We could factor out a sine squared and then take its square root. So outside we'd have 4 sine phi. What would we be left with? We'd actually be left with a sine squared plus a cosine squared inside, which is just 1. So it's just basically gone, which is actually extremely nice. This just simplifies to this right here, d theta, and we can ignore the wedge now since we're done with orientation ideas there, putting them together. So really the integral is just simply this one, where we go from 0 to 2 pi for theta, and here we go from 0 to pi thirds for phi, when we're thinking of the top cap of the sphere. So then in integrating this, the integral with 0 to 2 pi, the theta just multiplies 2 pi onto everything. And then we have, so basically that's going to be factor up to 4, so you'll have 8 pi. And then we're basically looking at this integral, 0 to pi thirds sine of phi d phi. Okay, that's going to be equal to 8 pi, and then we have negative cosine phi, so it's multiplied to pi, from 0 to pi thirds, which ends up being the calculation. This part is actually just a half. So we get 8 pi times a half, which is 4 pi, as we got before. So we did this in using a different method, but really it's the same thing. We're finding the same magnitude of the same vector. We just rewrote it in terms of thetas and phis and factored out the d theta d phi here. But really, we were just looking at the magnitude of the vector of aerial projections again on the surface, and we again got the same surface area for that top part of the sphere of radius 2. Thanks for watching.